Okay, all right. Yeah, I will send you email about that. So let's move. Continue moving. So only 2 weeks left of classes. It means that 4 lectures, right, left. Actually, 3 lectures, because there will be 1 exam. Oh my God. All right. Anyway, so where we are in terms of our material. So we started discussing coupled oscillations, right? So you have a system with n degrees of freedom, right? It's a conservative. Then transformation equations are time independent, right? You saw transformation equations were trivial, right? And we introduced a new set of generalized coordinates, which are just displacements from the equilibrium positions, right? Etas. All right, and as a result, we needed to write down Lagrangian kinetic energy and potential energy in terms of those small displacements, right? And as a result, we could use Taylor expansions. So that's why we expanded kinetic energy, potential energy, and we ended up and we introduced matrices: kinetic energy matrix, or sometimes it's called mass matrix, and potential energy matrix. They both are real and symmetric, because of the way we introduce them, basically by their definition, right? All right, and then of course we wrote down Lagrange equations, right? And then we search for a solution. Very important point: we search for a solutions, those oscillations, basically, right? Solutions, those oscillations, when and where the whole system oscillates with exactly the same frequency. So we didn't put any subscripts next to omega, right? So we search for a solution in the exponential form, right? Because that's the easiest, right? And of course, we went into the complex world from the real world. Instead of dealing with sines and cosines, it's better to deal with exponential functions, right? So then we grab that functions. Basically, at that moment, from that moment, we can say that we were searching for special oscillations when the whole system oscillates with the same frequency. So we shoved that equation, that search for a solution, into the second-order differential equations, and we ended up with the set of algebraic homogeneous equations. And since those equations are homogeneous, it's possible to have a non-trivial solution only in one case. Again, it's a linear algebra. Of course, at some point you also learned that and proved that. So non-trivial solution only possible when the determinant of the system is equal to 0, right? And from that determinant, we can get those omegas. Only with those omegas, which we call eigenvalues, right? But those are just basically frequencies of normal modes. Eigenfrequencies, eigenvalues, right? So only with those omegas, that function can be a solution of the system, right? And then once you know those omegas, you shove them back into the eigenvector equation. You can get eigenvectors, and at that point we stopped discussing the procedure, and we decided to look at the properties of eigenvalues and eigenvectors, right? And I wrote down the eigenvector equation for mode K, and then for mode L. Then I applied a joint transformation on mode L, and we combined those two equations, right? And as a result, we ended up with this. So that's where we finished. We ended up with this equation. So 0 equals, then the difference between eigenvalues, I think the first one is K, lambda K minus lambda L complex conjugate asterisk, and then the product of column, matrix, column. Okay, a row, column. So it will be A, which subscript? L. Yeah. A, L, dagger, right? Adjoint. Then T and A, K. So that's what we ended up with. Okay, let me frame it because I will need it in the future one more time, or maybe closer to the end of the class, right? And I will try to keep it there. Okay, so now, all right, I told you. So now we need to look at properties of eigenvalue and eigenvector. First, I claim that eigenvalue must be positive. zero or positive, real and positive. Eigenvalue, right? Right, okay, so first I claim I will put a new bullet over here, right? And lambda k must be larger or equal to 0. And I will write must be, right? And now let's show it. Let's show it. Okay, I will probably write because it's sort of not very rigorous proof, but more like a justification. Okay, so let me grab my notes and write what I have in my notes. So I will write, so a stable system. What does it mean, stable system? It means that if I displace, for example, one particle from the equilibrium, it will try to come back to the equilibrium. It wouldn't just fly away, destroying the system. So stable system. So a stable system requires. Okay, soon I will have to change my marker. I already prepared it. Requires then, and again, you remember what is lambdas? They are omega squared. All right, so the stable system requires that. Okay, otherwise, I thought I would be able to squeeze. Otherwise, if omega I, okay, slightly, let me rewrite omega I, and again, I wrote exactly the same. Otherwise, omega I squared, if omega I squared less than 0, basically it's sort of like a proof by contradiction. If omega I squared is negative, which is lambda I, then what? Then omega I is imaginary, right? Then omega I would be imaginary, right? And if omega I is imaginary, let's look at our solution. You remember we search for a solution in a certain function, right? So our solution is this. So eta I equals some constant c, then the eigen vector I, and then e to the power of minus I omega t. Okay, now since we are talking about particular mode, okay, I can put a subscript here, I, because we're talking about particular mode. Right. Okay, so if omega is imaginary, we have imaginary unit here, imaginary from omega, you will get another -1, and as a result, you will end up with what? C times eigenvector and e to the power of plus, okay, now absolute value of omega times t. What can you say? What can we say about this solution? It's a runaway solution, because with time the value of eta is increasing. But you remember we assume that our system is stable, right? We assume that we want to get oscillations around equilibrium point, and this is destruction of the system. So for our stable systems, omega squared, which is lambda, must be positive. Otherwise, we don't have a stable system, right? Okay, again, it's sort of like a proof by contradiction, right? Not very rigorous, but it's enough in order to be convinced that this is true, right? All right, so it's a unstable system, runaway solution. All right, so runaway solution, and it means that unstable system. So this statement is correct, right? Okay, maybe I will frame it a little bit because it's important, right? And now the next one. Yes, so as a result, if a lambda is real and positive, so it means that this asterisk can be dropped, right? So I can write, so lambda L complex conjugate equals to just lambda L. Okay, let me frame it, and then in a few minutes I will come back. I will go back to that equation. Right. So just now I'm just exploring properties of lambda, and now properties of the of eigenvectors. Right. So now the second small bullet. So now I claim that K or L, it doesn't matter which I used actually. Let me. Oh, I use I. Okay, so now, okay, let me write like this, like in my notes. Y are A sub I real, right? Okay, now eigenvector. So let's write down eigenvector equation. We're going to rewrite that eigenvector equation many times, right? So you remember what is eigenvector equation? So it's a V acts on which subscript? K. Okay, acts on eigenvector K. It leads to eigenvalue K, then kinetic energy matrix, and times eigenvector, right? So this is the eigenvector equation, right? And now let's look at this equation carefully, right? So V, potential energy matrix, of course it's real. We discussed it in the previous class, just by the way we introduced this potential energy matrix. It's real and symmetric. Then T, exactly the same. It's also a real matrix consisting of a bunch of real numbers. Then eigenvalues, we just justify it's a positive and of course real. Also real. So if almost all factors over here are real, right, then these vectors, eigenvectors, must be, okay, not must be, of course they still can be, it's possible to have them, to make them complex. But that complexity will be in which form? In maybe some sort of like a e to the power of minus I or plus I xi. But it will be on both sides of the equations, which can be cancelled anyway, right? So there's no point over here. Again, it's possible to make eigenvectors complex, but there's no point. If you do that, people would look at you like, come on, what are you doing, right? What's wrong with you, right? Basically, right? And plus, what's the meaning of these eigenvectors? Eigenvectors consist of what? Just those small displacements, okay, amplitudes of the displacements, right? Amplitudes of the displacements from the equilibrium of all those n particles. Of course, those amplitudes must be real, right? Again, so it's not very rigorous proof, but I think it should be enough, right? Without diving too much in that boring stuff. So let me write. So AK, I don't write must, I will write should be real. Again, if you desperately want, you can make it complex, but it doesn't make any sense. Should be real, right? Okay, so as a result, what can we get out of this? Of course, we can simplify slightly this adjoint transformation. So L dagger adjoint transformation, you remember it's a AL transposed and complex conjugate, right? So if it's real, of course, complex conjugate can be dropped, sign of complex conjugate. So it will be AL transposed. Right. Okay, so now we can go back to this equation, right? Let me check, right? If I mention, yeah, this is good. Right. Only transpose left. And now we need to start imposing additional assumptions. So far, we haven't imposed any assumptions on eigen values. Now, let's assume that we do not have any degeneracy. You know what? Maybe let me first rewrite this equation, and then I will make those statements. Right. So let me write. So back to okay. Let me put asterisk over here and write it there. So back to that. Of course, now we can rewrite it. So it will be 0 equals to lambda L, oh no, lambda K. Lambda K minus lambda L and A L transposed T A K, right? Okay, so that's our now that's the equation adjusted. And now assumptions. So now I will put a big bullet, because now from this point there are two roots. First one, which I'm going to start using now, we're going to assume that there is no degeneracy. So all eigenvalues are different. Of course, all eigenvalues belonging to different normal modes, they're all different. No degeneracy. We will spend here, we will be here maybe like for 20 minutes, and then after that we will make second assumption. What if you have a degeneracy? What if, for example, lambda L equals to lambda K? So different eigenvalues belonging to different different modes, normal modes, equal. And then we'll spend some time learning how to handle that situation. But first, let's assume no degeneracy. So which way I wrote it here. Okay, so let me label it no degeneracy. Right. So it means what? If, of course, K is not equals to L, so it means that different normal modes, normal mode K and normal mode L, and they're not the same, different, right? And so, and lambda L is not equal to lambda K. No degeneracy. So as a result, what do we have here? Lambda L minus lambda K is not 0, but the product of this and that must be equal to 0. So it means that this product of columns, matrix, and row must be 0. So lambda K minus lambda L is not equal to 0. So in order to be this correct, so we have this must be true. Lambda L T, okay, L A L transposed T A K must be equal to 0. And that is our condition for orthogonality. It's orthogonality. So it means that eigenvector AL is orthogonal to eigenvector AK automatically. So we don't have to do anything. So pretty much if you solve part of the problem, you found those modes, eigenvalues, okay, which are eigenfrequencies, eigenvectors, and if you see there is no degeneracy, you can tell immediately that eigenvectors are perpendicular to each other, orthogonal to each other, automatically. So you don't have to do anything. With the case of degeneracy, of course, the situation will be more complicated. We will have to do some voodoo dancing in order to make those vectors orthogonal. But here, automatically. Okay, so let me write it down, and which is good, because effectively, what are we trying to do? We're planning to use these eigenvectors as basically as a basis for our general solution. It's sort of like in three-dimensional space. What do we usually use as the basis? We have three mutually perpendicular and normalized vectors, right? And then any other vector can be written as a linear superposition of these three vectors, right? So they are mutually perpendicular. Also, for the sake of convenience, we can normalize them. And then it's the most convenient basis to write any vector. And here, of course, instead of vectors, right, so we have n eigenvectors. And if they are perpendicular to each other, orthogonal, and of course we will also normalize them, it will be the most convenient basis for this solution, right? Okay, so that's why it's so important to talk about these vectors being orthogonal to each other, right? So now, okay, yeah, of course this must be framed because it's a orthogonalization, right? So let me write something. So this must vanish, right? And yeah, let me first write the statement. So eigenvectors corresponding to different eigenvalues are orthogonal automatically. So eigenvectors, so E/vectors, I'm just trying to simplify a little bit. Eigenvectors corresponding to different eigenvalues, to different eigenvalues are automatically orthogonal. Orthogonal. So we don't have to do anything. Orthogonal. Okay, it's time to change my marker. And maybe I can write it also in a component form. Why not? Right. So this. Or maybe I can squeeze it here, orthogonal component form. So it will be equal to 0. And then, so it will be A. Okay, let's use what, J? Let me look. Yeah, JK. JK. Right. Then the previous one, T must, okay, let's say IJ. So internal indices must be the same. And this one, A. Of course, I can put, if I use the tilde transposed, then it will be Li. But if I remove tilde and flip indices, I will get immediately the final result. So it will be IL, right? IL. So I said L and I wrote J. What's wrong with me, right? So L, right? So, and summation over only I and J. Summation over I and J. Because L and K, they just tells us which eigenvalues of which mode we use, right? So that's this equation written in a component form, right? Here it's written in a matrix form, of course, right? Okay, awesome. So they are orthogonal, and now remember, just 5 minutes ago I told you that it's also convenient to make these vectors, like in even three-dimensional space, or in this case, it's more convenient to make. It's convenient to make to normalize them. It's convenient to normalize them, and we can also demand normalization over here, normalization of these eigenvectors. Why? Because you remember our system of algebraic equations. And in order to have a non-trivial solution, we demanded that that determinant equals to 0, right? And if a determinant of a system of an algebraic equation is 0, it means what in the system? It means that if you have n equations, You can take any of those equations, for example, let's say the last one, equation number n, and you can write that equation as a linear superposition of the rest of the equations. It means that one of the equations is useless. Basically, it doesn't give you any additional information. So basically, you have a system effectively after demanding the determinant equals to 0. You have a system of n minus 1 equations with n unknowns. It's underdetermined system, right? So you cannot solve for unique values of eigenvectors, right? So we have some small degrees of freedom which can be used, right? And we can use that freedom in order to demand, okay, let's normalize our eigenvectors. Usually in undergraduate level course, we would say, okay, let's say that the first component is 1, and then relative to that component, you can write the rest of the components of the vector, right? But here it's more sophisticated, so let's just demand normalization. Right. Okay, so now on top of this orthogonalization, we can demand normalization. And let me write something about what I just told you. Right, okay, small additional bullet, right? Since eigenvectors cannot be determined uniquely, cannot be determined uniquely, right? Okay, let me write determinant was equal 0 of a system of the system. Right. So that's the source of that fact. All right, since the equation can be determined uniquely, so we have some freedom to demand normalization. Normalization. Right. Okay, so which is, let's say we have eigenvector k, ak transposed, t, ak equals to 1. So here we have, you see, different eigenvectors of L mode, K mode, and now K and K, right, of the same mode. So that's the normalization. And this is just 1. It's just a number. It's not the unit matrix. It's just a number. Right. Okay, of course, this must be framed as well. Again, it's not completely necessary, but it's nice because, again, then it's easier to work with a basis which is normalized as well. On top of being orthogonal, if they're normalized, then it's awesome. All right. Okay, I can also write it in a component form, just in case, right? So let's say, so summation, again, it will be over ij, and let me start from the end. So it will be a jk, then t ij, and then a. Again, I immediately apply transposition. It will be first ki, but if I switch it, it will be ik. Yeah, and it is equal to 1. So that's the that equation written in the component form. Right. Okay, so now it's awesome, but it would be even better if we can somehow combine this equation and write it as one equation. And actually it can be done, right? And for that we need to over here we have a column, here we have a row, column, row. But what if we combine all these columns, all these eigenvectors in one matrix, and we call it modal matrix. And when we do that, of course, instead of a column, we will have just a matrix, n by n, right? And then this equation and that equation can be combined, right? So, and that equation from the new equation will be obtained when you deal with diagonal elements, you will see in a second, and this when you deal with off-diagonal elements. So let's combine these two equations, right? Okay, it's now next small bullet. So let's combine these two equations. So that's the goal of this next small section. Right, in order to do that, of course, we need to introduce one of the most important matrices in this section, of probably after kinetic energy matrix and potential energy matrix, now modal matrix. Introduce modal matrix, because everything now will be around this modal matrix. And it will be introduced in this way. We're going to use symbol A, and it is constructed like this. So you take the first eigenvector and position it in the first column. Then you take the second eigenvector and position it in the second column, and so on all the way to the last eigenvector and position it in the last column. So that's what we mean by the modal matrix, right? Okay, I'm not going to write in the components, but of course or maybe I will write. Right, so so it will be A11, A21, and so on, AN1. You remember the second index tells us in which mode we are. In this case, it's a first normal mode, right? And then particle 1, particle 2, particle n, the first index, tells us the particle. So then A12, A22, and all the way to N2, and then all the way to A1n, A2n, and ANN. So that's basically our modal matrix. And so with this modal matrix, these two equations can be easily combined, right? And we'll have, as a result, we'll have A transposed T A, and it is equal to unit matrix. Again, if you want to convince yourself, write explicitly. And diagonal elements will give you this equation. Okay, diagonal elements of this unit matrix. And off-diagonal elements will give you this equation. Orthogonalization and normalization comes from the diagonal elements. Okay, unit matrix, of course. Right. Okay, probably I should write, of course, this 1 equals to 0, 1, 0, 0, and so on. Then 0, 0, 1, so, and so on, and 1, right? So the unit matrix, right? Okay, this, of course, must be framed. And now, it's a kind of exciting moment. It looks like, we see that this matrix A, modal matrix, diagonalizes kinetic energy matrix or mass matrix. Diagonalizes because now we have new matrix which is a diagonal, right? And actually, this is the typical transformation in the in linear algebra, and it's called congruence transformation, right? But anyway, I will write what is congruence transformation just in order to refer something from the linear algebra. But what about what's so exciting about this? So it looks like with this modal matrix, we can diagonalize kinetic energy. And of course, at this moment, it should trigger your, I don't know, curiosity. What about potential energy? Is it possible with the same matrix A, this modal matrix, also to diagonalize potential energy? Why are we so interested in that? Because Lagrangian, it's a T minus U, kinetic energy minus potential energy. And if we can diagonalize both of these matrices with this matrix A, then your Lagrangian is going to be diagonalized. And what's so important about diagonalization of the Lagrangian? Because then Lagrangian is decoupled. Because all these off-diagonal elements, they give us coupling. And if we don't have off-diagonal elements, we don't have coupling. Lagrangian is completely decoupled. It means that if you write Lagrange equations, you will have a bunch of independent, uncoupled, right, decoupled, right, equations, second-order differential equations. It means that instead of dealing with a system, coupled system, where motion of each object is affected by the motion of the rest of the objects, in those new coordinates, you will have, instead of a system of instead of coupled system, you will have a system of n decoupled or uncoupled, right? Simple harmonic oscillators. What can be easier than that? So that's why at this moment, it should, I don't know, your heart start pounding, right, kind of in anticipation of significant simplifications, right? So because it's it will significantly simplify your life in the world of coupled oscillations, right? So now it naturally triggers. Let's look, is it possible to normalize potential energy matrix at the same time, right? And again, what does it mean that you do this, right? It means just you basically change your coordinates. Instead of using these coordinates, with this matrix A, you can change your coordinates, right? I don't know, rotate it somehow, do something, right? And then in those new coordinates, your kinetic energy matrix will be diagonalized. Will have a diagonal form, and potential energy matrix will have diagonal form, right? Again, it's basically about transformation, transformation of coordinates. All right. Okay. So now, okay, I can write also in a component form, since I kind of develop a habit here, component form, there, component form. Now I can write for this equation also component form. All right. So unit matrix, it will be just symbol Kronecker, delta IK. I think I use no LK. Okay, why not? Delta LK equals, right? And then now it will be A. K must be outside. K, and let me use J, I think, yeah? J? Yeah, J. Why not? Then the next T, it will be J, I, for example, right? And then this, of course, immediately I impose transposition. All right, so without transposition, I should have here I and here this L. So it should be Li, but if I impose a transposition immediately, it will be IL. IL, right? And so summation, right, over I and J. So in a component form, this equation, right? Okay, so I can write so that modal matrix A diagonalizes the matrix T. So I can write that A diagonalizes T. Right. Okay, it's important. And okay, as I said, I promised to write you that definition of congruence transformation, because this is effectively special case of a congruence transformation. Okay. It's not that big a deal, but if, for example, you want to, I don't know, read more about that, you can dive into that part of linear algebra and read. Right. Okay. So let me recall the congruence transformation. The congruence transformation, which is basically you act with your matrix A in the same way on some matrix T, and as a result, the form of that matrix changes to some new value T prime. In our case, it's a unit matrix A. So this is, in general, congruence transformation. Right. So now, okay, now let me write what about potential energy matrix. So now, since Lagrangian is kinetic energy minus potential energy, and of course the logical question I just told you, right? Can we diagonalize V also? Can we diagonalize potential energy matrix with a question mark? Right. In that case, Lagrangian, if yes, then Lagrangian will be decoupled. If yes, then L will be decoupled. And then, of course, differential equations will be decoupled. Differential equations will be decoupled as well. And which is, of course, significant simplification. All right. Okay, so now let's show that we can diagonalize potential energy matrix. Okay, now I think I have to erase all this, right? Okay, I can look at my notes if I need something. Okay, let me stop here. Right, so now diagonalization of V. And again, let's recall our eigenvector equation. Right, again, eigenvector equations. So let me write that. So it's a V acting on AK equals to, I think I use K, which index? Yeah, lambda K T A K. So again, it's a, okay, let me write eigenvector equation. Right. Which we got in the previous class. And now I just keep using it more over and over. Right. You know what? At this point, I need to write in the component form. And actually, because of this, I kept writing in the component form. Right. So it will be on this side in the component form Vij Ajk equals to lambda k T. Okay, let me write immediately here A. Okay, let me use JK, and here it will be ij, right? So that's the component form. And to emphasize that in this equation, k, there is no summation over k. K is fixed. Basically here, these are columns, right? Columns, so k is fixed. Right. So let me emphasize on that. So over here, k is fixed. So here summation over I and j. So basically it's a eigenvector equation written for the normal mode k. Normal mode k. Right. And so now if I write, for example, explicitly, so I can write equation for normal mode 1, this equation for normal mode 2, and so on. Let me write a few of them, right? For example, let's say I can write for k equals 1. So it will be first, of course, the matrix V11, and so it will be VNN. Then this is column A11 and all the way to N1, right, equals to lambda 1. And then, of course, there will be matrix for T, and then column again A11 and all the way to AN1. Then I can write the same for k equals 2. Again, there will be matrix V. Then again, column, but now it will be A1, 2, and all the way to more space, N, N2, and then lambda 2, again, matrix T, and then column will be 1, 2, and all the way to AN2, right? And then I can, of course, keep writing, and of course, the last one, k equals n. Again, it will be V, column, lambda n, T, column. Writing something like this over and over again, it's ugly, right? Of course, it's not pleasant at all. So that's why our matrix over here, again, modal matrix A, will simplify our life tremendously. So basically, let's try to combine all these equations with one equation, where instead of just columns, we will have a modal matrix A, n by n, because otherwise it's just kill me, right? It's ugly, right, procedure to deal with that. Basically, that's naturally matrices appeared, right, in order to simplify life of theoreticians, right? Otherwise, number of rewritings will be enormous. Okay, so now, as I said, now let's release this k. So here k is fixed in each of these equations, but now if we loosen up this k, we should be able to introduce the modal matrix, right, naturally into this equation. Okay, so now let's do it. Okay, first I will write, let's combine these equations. Let's combine all these equations, right? And in order to do that, our AJK, which is column, okay, where k is fixed, we will introduce the modal matrix, right? A, of course, in a component for jk, and now k is not fixed. Now k is not fixed, and of course, this gives us a modal matrix. Okay, let me write A11 all the way to AN1 all the way to N1, no, 1N, and all the way to ANN, right? So modal matrix. So basically, from this column, we can move to this matrix by releasing k, loosening it up. right? And now this component form, let's rewrite again, assuming that K is no longer fixed. Okay, let me do these manipulations. All right, I will just rewrite it, but again, K is not fixed, is no longer fixed. So V ij, okay, ij, aj k, then lambda k, and tij and ajk. Again, K is not fixed. K is not fixed, is no longer fixed, right? Okay, now some reasonably simple manipulations. So what if I write this matrix A, J, K in this form? Basically, at this point, I want to see what should be the structure of this equation, in a matrix form. Because right now it's not completely visible. Which matrix should be first, which matrix should be last, except at the very beginning, there are no any options. A V times A will be, but what we're going to get on the right hand side, we need to get that. So that's what I'm trying to get to do. Right. So A JK, of course we can write it as A, for example, JL and then symbol Kronecker, right? So it will be LK, right? And then this delta LK I can combine with this. All right. You know what? Maybe I will do it as the next step, right? Let me do it. Let me rewrite it. So it will be TIJ, AJL, AJL, and then I combine this lambda K with this delta LK. And introduce the new matrix. Basically, delta L K, it's basically this unit matrix. Delta LK, it's a unit matrix. So if you take lambda K, K is no longer fixed. It runs from 1 to n. So if you multiply it by this, you will get all those eigenvalues along. They will be diagonal elements. Right? So now let me introduce this new matrix. Okay, let me open my explanation box. And lambda LK new matrix, which is lambda K delta LK. Right. And I can write, so this matrix, this is the matrix lambda, which has this structure, lambda 1, 0, 0, 2, 2, 2, then 0, lambda 2, and then so on, all the way to lambda n. So we can introduce this matrix, right? So now, as a result, let me rewrite this equation now in using this. So it will be T I J A J L and lambda L K. So now we have structure which we wanted. So we have L internal index, J internal index, and here everything was good from the very beginning. So now I can see the structure of the equation. So it will be V times A equals to T A times lambda. So now I can see the structure of the equation in a matrix form, right? Okay, so now I need to invade this part. Right. Okay, let me stop at this point. Yeah. So now I can write, it will be, where is it? T, I mean V times A equals to T, A, and again, this is the matrix. Sometimes you can put a bar underneath, right? Emphasizing that that is the matrix. Okay, so what can be done now? On purpose, I stopped at this point because now I will need this equation. What if I multiply this equation by A transposed from this side? Right. What if I multiply it by A transposed, both sides of the equation? Of course, I will end up with what? A transposed V A equals to A transposed T A and our matrix lambda, this matrix, right? Okay, so what can we say about this construction? A transposed TA, it's a unit matrix. All right, so as a result, it is equal to just lambda. So what are we getting? Okay, let me rewrite. So A transposed V A equals to lambda unit, I mean not unit, diagonal matrix. You see, it's a diagonal. So we can frame it. And again, what is this effectively? It's our congruence transformation again, but of course now performed on V, not on T. Right? Again, it's a congruence transformation, and we are getting again diagonal matrix on the right hand side. So it means that we are, and with the work of the same modal matrix A transposed A. Here we also had A transposed A, right? So both matrices T and V can be diagonalized with the same modal matrix. Basically, we can say they can be diagonalized simultaneously, basically at the same stage, at the same step, at the same stage. Okay, yeah, it's great. So it means that Lagrangian will be decoupled. Okay, diagonalized and decoupled, right? In new coordinates. Right. Okay, so now let me frame it. Okay, I did, and now let me write conclusion. So A diagonalizes V with eigenvalues. Yeah, and of course, yeah, I forgot to mention. Of course, again, as diagonal elements, we have our eigenvalues. Of course, it should be stated explicitly. So let me write that down. So A diagonalizes V with eigenvalues as diagonal elements. Basically, I can write so it is simultaneously. Oops. Okay, simultaneously with T. So we can diagonalize potential energy matrix and kinetic energy matrix, right, simultaneously. Okay, and of course the last. All right, so L, which is T minus V, right, is also diagonalized. So A, or I can say A diagonalizes L as well. Probably let me write this way. Yeah. Right. So A diagonalize L, which is T minus V, right? Which is very important. So now let me probably, you know what, I'm not going to write these properties of modal matrix. I will just state them. So first, again, so how do we construct modal matrix? You take all eigenvectors and position them as columns. Then, second, we proved, and I erased it, right? That eigenvectors in this case are mutually orthogonal to each other, right? Because if, in the case of if there is no degeneracy, it means that all these columns are orthogonal to each other. It means what? What can you say about this matrix? It's orthogonal, right? Orthogonal matrix. And one of the properties of orthogonal matrix, if you transpose it, it is equal to inverse, right? And just some interesting facts. Let's call it this way. All right, and of course, yes, we just saw this modal matrix diagonalizes both kinetic energy matrix, potential energy matrix, right? And of course, as a result, Lagrangian is diagonalized. And of course, also, as we declared at the very beginning, all elements in this matrix are real, because basically these are eigenvectors. And we showed at the very beginning of the class that vectors, eigenvectors are real. Right, so now I promised to keep that equation, but I erased it. Okay, anyway, so at this point, okay, let's just leave it behind for now, right? These interesting results. And now we still have the second situation. What if we have degeneracy? Now we need to go back to this equation, or I still see the frame of that equation, right? So we need to go back to that equation, saying, what if we have degeneracy? What can be done in that case? Okay, first, what will be in that case, and then what can be done? How can we handle that situation? Right. All right. So I will erase this part. Yeah. And I think I labeled that equation with asterisk. Right. So now I will put a new big bullet, right? Okay, let me write, if there is a degeneracy. There is a degeneracy. Right. So back to that equation. So let me write, so back to that equation. Right. You know what? I need to rewrite it. So it was lambda, I think L or K first. Let me look at my notes. Okay, I have here. So lambda K minus lambda K minus lambda L equals to a K, I think, first one. Yeah, K transposed T A L equals to 0. So that was our equation. And now degeneracy. Again, what if K is not equals to L? So we have different modes, different normal modes. And okay, let me write the way I wrote. If this is true, and lambda L equals to lambda K, right? So that's degeneracy. So in that case, so what's the situation? Where the troubles are? Okay, probably I need to again frame this. Right. And the troubles is this. So now this factor lambda K minus lambda L is 0. So basically this factor guarantees that this equation will be correct. And then it doesn't, the role of this product is not that important, it looks like, right? So I cannot say, for now, I cannot say that this will be equal 0. Maybe by accident. by accident, right? This product of this column, matrix, and column can be 0. But it's not enough for us, because what we wanted, you remember, we wanted we want to have we want to have orthogonal eigenvectors, right? We want to get orthogonalization, but now we can get that only by accident. But of course, we cannot rely on the accident, right? It's not like in the previous situation when this was not equal to 0, and then of course this equation can be correct only if that is 0. Immediately, automatically, we were getting orthogonalization. But now we don't have that privilege. So now we cannot tell that AK is perpendicular to AL. Again, unless it happens by accident, which is still not impossible, but not enough, right? So now let me write that. So, all right, so AK transposed T AL is not okay, let me write, is not 0. So we cannot say that they are perpendicular to each other. So we cannot say that AK and AL are orthogonal. So as a result, so you see the problem, and now what can be done? Yeah, of course, we can, as usual, we can sit and cry, right? But there's a typical procedure which can be applied in order to handle that situation. And I'm sure that most of you remember, right? It's a Gram-Schmidt procedure, right? Which can be applied to diagonalize any elements. For example, let's say you have n some functions. And let's say you introduce some procedure which can be used to, which defines orthogonalization. Of course, it depends on the space, which elements depends on the space, and you can introduce orthogonalization any way you want, right? Let's say you defined orthogonalization, and then if you apply Gram-Schmidt procedure, out of those n functions which are not initially not orthogonal to each other, you can create a new set of n functions, but now they will be all mutually perpendicular to each other. You can apply, as I said, to any elements, as long as you define what do you mean by elements being orthogonal to each other. And of course, that definition can vary, right? In our case, we define it over here somewhere. I erased it, right? Right. Actually, it was this equals to 0. That was the definition of our orthogonalization, right? Okay, simple example, for example, from two-dimensional space with two vectors, in order to see what does it mean to apply Gram-Schmidt procedure. Okay, so let me first write the title and then that simple example. All right, so we can apply Gram, okay, let me spell it correctly. Yeah, Gram-Schmidt, sounds like German, Gram-Schmidt procedure. And again, the idea is what? Instead of these vectors AK and AL, which are not orthogonal to each other right now, we can construct a new set of vectors. Okay, in this case, two vectors, which are going to be orthogonal to each other. Right? Okay, simple example. Example from 2D space with two vectors. So let's say, maybe I will, okay, let me draw it here. So let's say we have two vectors, vector A and vector B. So you see right now A is not perpendicular to B, but we want to get two vectors which are perpendicular to each other out of these two. So the typical procedure. First, you need to make a decision which vector, one of these vectors you can keep. You can start from that vector. In this case, it's better. Let's keep vector A, and then we will find the second vector which is perpendicular to vector A. Right? So let me write. So first, keep A, and of course, let's for the sake of convenience, let me introduce the unit vector. Unit vector in the direction of A. So U hat equals to A divided by A. Okay, vector A divided by the magnitude of A. Then, oh yeah, let me show first this vector A, right? So, I mean, not vector A, U, vector U. So this will be our vector U hat, right? And then, what if what if I find this component of this vector B on the direction of A? So this length, how can we find that? It will be dot product of B and U. B and U. Oh, it's already, just a second, let me at least finish this, right? B and U, so it's a magnitude of this, basically, component of this, yeah, component of B on A. But I want to introduce it as a vector. So in order to do that, I need to multiply this by, okay, let me write U hat. So now that's this vector. And now if we want to get a vector which is perpendicular to A, which is this vector, right? Let me call it V. So how can we get that? From this right triangle, we can easily get expression for V. V will be equal to what? You need to take B and subtract this newly introduced vector. So B minus B dot U, it's a unit vector, and times, times U hat. Yeah. So this now vector V is perpendicular to U, but of course, if you want to even normalize it, of course, you can easily normalize this vector V and introduce V hat, which will be vector V divided by magnitude of V. So now you have a normalized vector U, which is perpendicular to the normalized vector V. So that's the basic application of a Gram-Schmidt procedure for the simplest possible case of two vectors in two-dimensional space, right? So something like this we're going to do next class in order to find or introduce, instead of these two vectors, eigenvectors AK and AL, two new vectors which are perpendicular. Again, like here, first I will keep A sub k, right, like here I said. And then I will construct a new vector instead of AL, which is going to be perpendicular to the first one, A sub k. Right?